Thank you for that introduction. Hello, everyone. My name is Markus Gusenbauer. I'm working at Danube University Krems in Austria in the Center for Integrated Sensor Systems. And today I will talk about sensing the blood cell damage in a magnetically actuated circular pump, which we could develop thanks to our sponsor, the Austrian government. Well, the project started with a problem. We wanted to develop a pumping system with reduced cell activation. So why do we need this? If you take a blood sample, the blood cells get a completely new environment. They get new temperature, new chemicals, new pressure. So they start to change their expressions. They get inflammatory reactions. And if you want to analyze blood cells outside of the body, it's bad because they change. Maybe if they get to the microscope, they are completely different than inside the human body. So every step from taking blood sample to the microscope should be optimized in order to reduce the cell activation. Well, our solution was, first of all, to obtain design guidelines by simulations and then, of course, building the device and then validate it with hemolysis measurements. And the overall goal of the project in the end was that we not only want to measure the cell activation in the pump, but also in different devices, as I said, from taking the blood sample to the microscope. Well, here's the schematic of the pump. We have a circular channel. The overall diameter is about 8 centimeters. There are two plugs. There are hard magnetic spheres. They are about 7 millimeters in diameter. And it works like this. A is blocking in and outlet, and B is moving like this. And if B comes close to A, they switch the position. B is the new blocker, and A is now the new driving motor. And just recently published the paper. Well, the idea is not new. In 2001, Hedge et al. Published a ferrofluidic magnetic micropump. This is much smaller than in our case. They used a rotor in the center and they were moving ferrofluid. So if the ferrofluid comes closer, it connects with the upper ferrofluid. And if the rotor goes further, the ferrofluid separates again and we have again a driver. A similar approach, but we have much larger scale and fixed permanent magnets. Well, we do not use a rotor, we use electromagnets. We have 10 electromagnets, which we can control with an Arduino control unit. So each electromagnet can be controlled individually by voltage and current and the timings. So we can define the position and the speed of the two plugs. So here is the demonstrator, the first demonstrator that was working. You see that here's always one plug blocking in and outlet, and the other one is driving the fluid. So what now with the cell activation? So if you imagine the plug cannot be as the same size as the channel cross section. So we need a certain leakage, which in fact is good if you want to pump blood. So imagine if there is no gap at all, the cells would be squeezed, there would be really high cell damage, but of course the pump performance is good because you have no leakage in the pump. But if you imagine a large gap, here we have low shear forces, so less or low cell damage. But of course there's bad pump performance because we have lots of leakage. So there is some optimum with moderate shear stress, moderate cell damage, with still quite good pump performance. This was our goal to find. You have some simulations. These are typical Navier-Stokes fluid dynamic simulations. We have the plug in the center and the streamlines around. So we have at this dashed line, we have the cross section. We have several scenarios. We have a centered sphere. This is the idealized sphere because in reality it just on one boundary on top or bottom, so like this. And we also have some assisting trails here that keeps the sphere in the center. And if you look on the right plot, you have the position. So here is just one streamline here, and here is the position of the sphere. And exactly close to the sphere, there's really high shear stress. And this is bad for cells, because shear stress leads to mechanical stress on the membrane. And if the stress gets too much, the membrane can break and hemoglobin is released, so the cell is dead. Well, and there's an equation. This is the blood damage index. Here we can compute we can estimate the hemolysis index. So the hemolysis index is just shortly, it's just the amount of hemoglobin released in plasma. Every cell that breaks releases hemoglobin, and this is measured. So we have the average of all lines from inlet to outlet, and we have some constant C. We have the small time steps of every streamline and the constant shear stress at this time step. And with such an equation, you can estimate the hemolysis index. Here's just some examples from literature. It's done quite often. Here are some rotary pumps, different scenarios, but they all do the same. They create streamlines, they compute the shear stress along the streamlines, and they estimate the hemolysis index. So now in our case, we have now here a plot. Here is the gap size. On the left side, we have the blood damage, and on the right side, we have the flow rate. And if we have no gap at all, or a small gap, the simulations, we need at least a small gap. Well, we have rather good flow rate, but also the blood damage is high, as expected. But in this case, the cell squeezing is not taken into account, because the Navier-Stokes equations cannot incorporate cell squeezing. If we increase the gap quite much, we have a large gap, then the flow rate is only half of the best performance, but of course also the blood damage is low. So at some point there is some optimum which you want to find out. Well, we came up with a gap size of 0.2 millimeters that should be optimal. We were driving the pump with about 70 cycles per minute. This got us a flow rate of about 8 milliliter per minute without an applied load at the outlet. So if you apply a load, the flow rate will be less than 8 milliliter per minute. So from the computation, we got from one circulation, we got a rather small hemolysis index, but multiplying it by about 19,000 circulations in 4.5 hours, we got an hemolysis index of 0.09. And in comparison to the experimental hemolysis measurement, so here again, the free hemoglobin is measured. After 4.5 hours, we have 0.16%. So this is almost 2 times higher. Well, we think that this is because of the missing cell squeezing effect that is not taken into account in the simulations. But we are interested in what's going on in more detail. So just 2014, we developed a model of red blood cell. So here's the model. It's just a membrane that's with 400 interacting nodes. So it's just some spring constant that can be tuned. So we incorporated this blood cell into the Espresso software. This is an open source software. So if you're interested, you can download it and try it on your own. So what we are interested in was then the change of surface area. In this case, S is the surface area at the current state, and S0 is the relaxed state. We're always looking at the change of local surface area. Here we start just to demonstrate what's going on. The red blood cells start with blue, so if the surface changes, they get red. You want to squeeze through some cylinders, and after they squeeze through, they go back to the blue state again. And just recently we thought, okay, we should use this model to see how much blood damage is in microfluidic systems. So here we have a similar equation. We have n cells, so we average over the cells from inlet to outlet, but this time we look at the change of surface area. So this equation is just schematic, so just to get an idea on how it works. And compared to the blood damage computation, we have one time local surface area of single cells, and at the other time we have shear stress information along path lines, which should or maybe not will be the path line of the blood cells. So we are not at that point that we can say our model works better than this one, but we are on the way. Well, here is already a conclusion. I showed you a new cell channel pumping device. We performed blood damage computations and compared it to hemolysis measurements. We have seen that in experiments, the blood damage is 2 times higher than in the simulations. So we decided to improve the theoretical results with the cell damage index to really get the information of individual blood cells. And in the end, our goal is to sense the stress in different devices to optimize the pathway from taking blood samples to the microscope to not changing cells too much. So thank you for your attention. Here are the group members from the modeling and simulation and environmental sensors group. Thank you very much.